what's changed since then. And this is a really neat study done by Camilo Mora and colleagues out of Dalhousie University. And what they have discovered is that there is a testable way to go about estimating these numbers, rather than pulling them out of a hat or asking an expert what they thought, which is basically the way it was done before. So, if you don't know, when we classify something, we give it a species name, but the species belong to a certain higher group, known as a genus. And all the genera belong to a certain family, and it works itself up until you get to the highest group, which is known as a phylum. And within the whole animal kingdom, there are only 32 of those, not that many. So we have this pyramid-like scheme on how things are classified. And when you actually look this in numerical context and put this on an exponential scale, as you see here, there is actually a neat relationship in terms of how the numbers increase from a phylum as you go up to genus. But where it breaks down is when you get to species. And it's of course because we have certainly not described all the species. We really don't know how many species there are. But what they did is they looked at rather well-known groups to see whether this relationship, as it's predicted, holds true for the well-known things such as fish, birds, and mammals. And it does. So they basically ground truth this method. And so we now can use this as a yardstick. So what did they come up with in terms of actual number? 8.7 million plus or minus 1.3. That's still a lot better than what we knew before, yes? Sure. It also tells us that 86% we don't know yet. That's what we know. So we got a long ways to go. But now we got something that we can use as a measuring stick. How about marine stuff, right? Census said 1 million plus. More et al. Says baloney. At least twice as much. 2.2 million plus or minus 10%. It means that we actually know there are a lot more unknown species out there than we thought. It's basically 1 in 9 rather than 1 in 3. So, the other interesting thing is when you break this up by the different kingdoms, which are listed here on the left side, and then look at what's known and what's unknown. The plants, they are probably the best known group. We know about 215,000, and they predict about 298,000. So there's only about 28% left based on that model that we don't know. You compare that to some of the others, such as fungi, pretty amazing. What is it, 93% are unknown? Animals also, a very high proportion. So it really depends on the group. And plants are probably one of the best known groups. Before it was 3 to 100 million. Now it's basically, if you put the up on that, 8.7 plus 1.3, a max of 10 million. And 2.2 are marine. So somewhere between a fifth to a quarter of all species are marine. So in terms of answering the alien, the friendly alien, is that in terms of magnitude, we're pretty sure it's 10 million. Not 1 million and not 100 million. And 2 million of those are marine. That means that for every known marine species, there are actually still 9 unknown out there. So ladies and gentlemen, the age of discovery is still at hand. What we're going to try and show you is some of the species don't really fit the group that they usually belong to, that you think they look like, or things that you simply are unlikely to have found before.
This is a show and tell. That's all this is. There's no exam. Just I want to show you some remarkable adaptations of just a few of our Canadian Atlantic fishes. And I'm going to start with the deep sea because that's where some of the neatest stuff is on. The deep sea. This is, you saw Gerhard's wonderful map of the continental shelf, continental slope, and this. Deep sea begins at the end of the continental shelf, 200 meters and down. And when you get down to 200, 400, 600, 1,000 meters, there's virtually no light. And meals are few and far between. So fishes have to find a way to capture those meals and hold on to. This is an ogre fish, or a fang-tooth. This fish has big teeth. And that's how it captures and holds on to the meals when it encounters them. And there's an actual specimen down below. It's, you can see those are big chompers. So, and it's well adapted to finding those meals, to holding on to those meals. Fish, I believe, has relatively the largest teeth of any fish, relatively. Well, it shows up there better. I'll show you the specimen in just a minute. This is the viper fish. The teeth are so large they don't fit inside the mouth. They actually fit outside the mouth when it closes its mouth as much as it can. So here's an actual specimen. And these teeth are enormous. When it encounters a meal, it's going to hold on to it. These things feed mostly on small fishes, also on crustaceans, maybe some small squid.
Are these samples from local waters?
These are from the Canadian Atlantic. These are found on the slope of Nova Scotia. Yeah, and not in the Bay. Interestingly, this species has another adaptation to help its feeding. If you look first at the illustration at the top, you can see that first fin ray, the dorsal fin, the top fin on the back, curls over in front of the mouth, and you can see it a bit. Well, do we have a pointer? Sure. On the lower one, follow it back below that ruler, and you can see that on this bottom.
Oh, yeah.
Follow that back, it keeps going, it keeps going, it keeps going. Usually they break off and capture, but what that is, it's a fishing lure. Remember, they live where there's no light. On the end of the fishing lure is a light organ. They dangle that in front of their mouth, lure things to it, and then with those teeth, very effective at feeding. This is a very unrelated fish, distantly related, but it also has a fishing lure. And what's happened through evolution is that first dorsal fin ray has moved forward to the tip of the snout. Again, this lives in the deep sea. The end of the fishing lure is a light organ. That lure, or the whole thing, is almost 3 times the body weight of the fish. And it looks like it should be able to fly fish with that thing. Put it right out there. But it can't. It's got a solid structure up about as far as vertically as you can see. But after that, it's soft. And it can hang it out in front and twitch it in front of its mouth. So just a little fish, right? Here's the end of the lure. So that gives you an idea of how long it is. And this one actually has the intact light organ, which that doesn't. But there's the light organ that it uses on the end of that long lure to attract prey. I'm going to show you loose jaws. Concentrate on the adult for now at the bottom. This fish has a very long lower jaw that it can actually thrust forward and spear its prey with the big teeth. So that's how it captures and holds on to prey. Interestingly, there's no floor to the roof of its mouth. That's why it's called a loose jaw. So it doesn't have the drag of a big, wide open mouth when it tries to thrust the jaw, which would give a pressure wave and warn the prey and swim off. So it can thrust that thing very quickly since there's no floor to the mouth, like I said. An actual specimen. See, there's no floor to the roof of the mouth, to the floor of the mouth. There's no membrane. There's only the ligament that connects the symphysis of the lower jaw to symphysis of the clypeus. The upper illustrations show larvae. If you look at figure C, you'll see that the intestine is far outside the body, like equal to the amount that's inside the body. Now, we can only speculate as to what's the advantage of this, but it's likely it gives it better capability for digestion and absorption. It may also increase the variety of prey types that it can digest. Here you can see where the intestine leaves the body and it meanders along, and it goes right on the screen, doesn't it? So, there is the anus, way out there.
Not a damaged specimen either.
No, it's not a damaged specimen. That's a good point, because sometimes the intestines rip off during capture. No, that's an intact loose jaw as a baby. Flatfishes in general, as I'm sure all you know, flat. And they also have two eyes on one side of the head, and they lay on the bottom like this, so they don't get mud in their eyes. The eyes are on the top side. And you know, they swim like this. But all flatfishes, as larvae, are like any other fish. They swim like this, they have one eye on each side of the head. And with metamorphosis, when they change to juveniles, in general, one eye moves over the top of the head to the other side, and they change their orientation. It's got this large thing on its head, cartilaginous rod. Nobody knows what it's really for, so we can only speculate. Speculation is it may be a rudder that it uses to help steer, or it may be like more like a keel that keeps it straight when it's doing its undulating swimming. Maybe that it just makes the thing look bigger, which deters predators. Predators know the size of the mouth. If something looks too big, they're not going to take it. Now, with that standing up, that spine standing up, it would look much bigger. It's not to make it look scary, it's just to make it look too big. This comes into our waters in the warmer months, into the Bay of Fundy. The adult is huge. I mean, up to over 3 meters. Now, mostly 1 to 2 meters in our waters, but up to 3 meters. The babies hatch from the eggs at 1.5 millimeters. Big difference. But what's more remarkable is they look different. And you can see the larva up there looks not like a pincushion, because it's not thin spines, but it's covered in ridges with spines on it. I don't know if this will work or not. It's coming, it's coming. You notice that the larva has a well-developed tail on the right-hand side. With metamorphosis, this tail really shrinks and is absorbed, so that it's just vestigial, though it is still the main means of propulsion in this huge fish. They get very pot-bellied for a while. The tail is now like this. It's kind of, it loses that too, as you can see. These were once thought to be the largest planktonic organism, because the biggest ones were seen at the surface, just floating along, not much swimming ability. All they could eat was jellyfish, all they could catch. Turns out they were the really old, sick, parasitized ones. This is my favorite larva. Okay, first the adult. I do have an adult. It's a typical deep sea fish. It's black, it's got big teeth. Well, which you can see there, but that's an illustration. It's not a real specimen. It is a real specimen. Very toothy. Long, thin. That's your average size. They do get up to nearly half a meter. The interesting thing about this larva is the eyes are way out on stalks coming out the side of its head. Those are its eyeballs out there. Those stalks are 1/4 of the body. And they can control those stalks, so they can move them around and see things. So that greatly increases their field of view, and it doesn't create pressure waves to alert prey, so they're more successful feeding. And predators don't feel those waves and say there's a fish there, because the bodies don't move, just the eyes do. And perhaps they can see a predator behind them. No, I don't know. Makes sense. They also have the gut that comes outside the body.